Isotopes, so we understand the relationship to radioactive decay. So this should be a review, should be easy, this first part, before we get into the newer stuff. Hopefully you remember isotopes are when atoms have the same number of protons, but different number of neutrons. And remember, that would only affect its atomic mass, because protons determine what element you have. So just a quick review of the atomic notation. Remember, this would be your symbol. It could be oxygen, hydrogen, helium, whatever. Then you're going to have two numbers. Sometimes they're reversed, the A and the Z, but the bigger number will always be the atomic mass, because that's the number of protons plus neutrons. And the atomic number is just the number of protons. So in this example here, the chemical symbol for C is carbon. Atomic number is 12. Atomic number is 6. Atomic mass is 12. So that means there's 6 protons. 12 minus 6 gives us the number of neutrons. So subtract these two numbers to find the number of neutrons. This case, 13 minus 6, there'd be 7 neutrons in this isotope of carbon. So this is carbon, but the only difference is this carbon has one more neutron in it. And 14 minus 6, this would have 8 neutrons, but still be carbon. So some isotopes, carbons, carbon 12, carbon 13, and carbon 14, only differ in the number of neutrons they have. If you look at these periodic tiles, the atomic number is 20.17, 107. How can we have a decimal? In other words, 20.17 minus 10 would be 10.1797. You can't have 0.17 of a neutron. So what these actually are is weighted averages, meaning you're going to have some neon 19s, some maybe neon 20s, some neon 21s, but the average would mean the average of all of them together that are found in nature would be 10.17, meaning the most common number of neutrons would probably be 10 for neon, because that number is so close to 10. Here, 6.94 minus 3 would be 3.941, meaning the most common number of neutrons for lithium would be 4, because it's so close to 4. Yes, some will have 3, but way more will have 4, so they weigh that percentage, and the most common would be 4. So isotopes can be named or identified by the notation we talked about, or we could just say that top number, carbon 12. It's a little easier, and we really don't have to say the bottom number, because we can look that up. The number never changes. So here we see different isotopes. Carbon 11, 12, 13, 14, 15 always have the same number of protons and electrons, so we just subtract 11 minus 6, mass, minus protons, to find the number of neutrons. More examples: hydrogen 1, hydrogen 2, hydrogen 3. 1 minus 1, 0 neutrons. 2 minus 1, 1 neutron. 3 minus 1, 2 neutrons. And I just said this, so I'm going to skip it. This shows it as a picture form. So we said they different number in neutrons for isotopes, and they also differ in the number their mass, because neutrons count as part of the mass. So the decimal thing I talked about, we said they are weighted averages of all the known isotopes. In other words, every isotope they've ever discovered, they kind of average them together. It's not possible to determine how many different isotopes exist when you look at the periodic table, but you can guess or figure out what's the most common based by the subtracting the atomic mass given in the periodic table minus the atomic number. This is not true in nature, but if it were true, if a third of them occurred as each of these, when you average that together, the atomic mass would be actually 2, because you have as many 1s, 2s, and 3s. I'm sorry, 0, 1s, and 2, so 1 would be the most common here. But that's not the percentage they actually occur. This is the percentage they occur. So in nature, 99.98% of all hydrogen is hydrogen 1, which has 0 neutrons. A very small percentage have 1 neutron, and even a smaller percentage have 2. So if you had 10,000 hydrogen atoms, 9,998 on average would be 0 neutrons. 1.56 would have 1, and less than a half of them would have 2 neutrons. So when you do some fancy math, which you're not going to have to do, this is the atomic mass you see in the periodic table. Notice it's almost 1 because 99.98% of them are. So the weighted averages means almost anyone you're going to find is going to have 0 neutrons and 1 proton. Here are the 5 naturally occurring isotopes of zinc. 34, 36, 37, 38, and 40 neutrons are all available. Here's their percentages. So notice about half of them have an atomic number of 64, and about half of them between 66 and 70. So when we do the math here, we get 65.39 because we have half of them are between 66 and 70 and half at 64. If you see parentheses on the periodic table and it shows, it's going to show the most stable isotope, meaning the isotope that's going to live the longest. And it's also going to tell you something we'll learn in our next slideshow. So we see here, it says the atom below lithium has 2 naturally occurring isotopes. Which of the 2 would have a greater frequency of occurring? Well, if we look here, this number is almost 7. 7 minus 3 gives us 4. We would also have, since it's not quite at 7, some with just 6. But this number is almost 7, so 7 minus 3, the most common would be 4, which makes the most common isotope lithium 7. So if we look here, naturally occurring uranium is a mixture of 3 isotopes. U-238, 235, and 234. Look at the percentage of abundance. So what's this tell us? It tells us almost all of them are at 238. So 238 would be the number atomic mass that we would be closest to. Doesn't mean it's exactly 238. It's going to be a little less, maybe 237.9, something like that. But it should be very close to 238 since almost all of the isotopes are that. And that radioactivity relates to this because it's the spontaneous breakdown of a nucleus forming a different nucleus, and it makes more particles. So basically it means it breaks down into something new. Nuclear equations, which we'll show in a second, show how it decomposes over time. In it, for instance, here, carbon-14, given enough time, will break down into nitrogen-14. How? It loses, well, first of all, it gains a proton, but it also loses an electron, and it's going to be a different element now. Nuclear forces are what hold neutrons and protons together to form a nucleus, and eventually they break down over time. There are different types of radioactive decay. We're not going to get into all those, just be aware. But each time we're talking about we start with one element, and it's going to change into something else. Here's a nice little decay series. You will have questions that show this, and they're not as crazy as they look, but the key thing to notice here is we're always going to start with the most energetic and least stable, and we follow a bunch. It changed to thallium, blah, 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 blah. Keeps changing, changing, changing. Whatever we end with is going to be the most stable. So each step down, we are losing a little bit of energy, but we are gaining a little bit of stability, meaning it'll last longer. Half-life is the amount of time it takes for half of the original sample to decay into something new. So here's some different ones. Radium-223 has a half-life of 12 days. These different isotopes of radium have different nucleotides. Look at this one, 1,600 years. So that is the most stable form of radium because it lasts the longest. But after these number of days, only half of the original radium would be left, half would have decayed into something else. This graph, there's going to be a question on this, is how it always goes. Over time, it goes pretty quickly, and then it levels off near the bottom. This would be one half-life. So after one half-life, we have half new stuff, half old stuff. Then half of this breaks down, so the 10 becomes 5 and 15. So now we're at a 1-to-3 ratio after just 2 half-lives. And then another half-life, we're at a 1-to-7 ratio, meaning only one of every 8 particles, there's 1 original and 7 new. When I say original, we're talking parent atoms. Parents are all these. And then the new atoms that form, the red ones in this picture, are called daughter atoms. And that will be it for part 1.